2, which means that x is equal, or x1 is equal to x4, and the x2 is equal to x4. Now I have a relation between both of them. x3 is missing, so it will stay. So that's the relation that I'm telling you about. For R4, I will have 4 coordinates, 4 components. That's the first, second, third, and fourth. Trying to separate them, you will end up having 2 vectors, as you can see, 1, 1, 0, 1, and the 0, 0, 1, and 0. Those are the 2 vectors represent the null space of this null vector space. Okay, now I have it. The null of A consists of the first vector, which is relative to x4, the second, which is relative to x3. Now, these 2 vectors with dimension equal to 2 represent this span, or the null span of A. Same way as before, look to the pivots of the echelon 4. If I look to first, the span of the row space is very, very simple, which is 1, 0, 0, negative 1, 0, 1, 0, negative 1. And the span of the column space, remark that the pivot of the first column already exists, so it's going to be the first column. The pivot of the second column also exists, so it's going to be the second column is the vector. So here's the row space, which is 1, 0, 0, negative 1. You will find it here, 1, 0, 0, negative 1. And the second vector, which is 0, 1, 0, negative 1. Here we go, that's the basis for the row. For the columns, I will take the first 2 columns only, because their pivots already exist in the reduced echelon form. So 1, 0, 0 for the first vector, and the second vector is, as you can see, negative 1, and 0, basis for the column space. Once more, if I want to check the dimensions, it will work. I have here how many columns, it's 4. So once more, if I want to check the dimension, here we go. M is equal to 4. The dimension of the null is 2, which equal to the dimension of row is 2 vectors. The dimension of columns, 2 vectors. The reduced, the echelon 4 consists of 2. So already the numbers are correct for the whole steps. This is how to go through your analysis, finding the null space, the column space, and the row space of a certain subvector space. Taking all of this into another level, so let A be an n by n matrix, and the A of x belongs to the column of A. I can look to this multiplication process as a linear combination of the columns of A with coefficients or coordinates to the entries of the vector x. So the multiplication of the matrix A times the coordinates of a basis of a certain subvector space can be represented easily. So if I want to have AX as a linear combination, if I considered X as the coordinates x1, x2, x3, multiplying A by X, it's exactly like multiplying the first column by x1 plus second column by x2 plus third column by x3. So once more, remark that AX is always a vector in the vector space of A, and it is a linear combination of A columns with the coefficients of the X vectors. This is the linear combination, and this is once more, don't you forget, this is the coefficients of a linear combination. So once you multiply this matrix by the x1, x2, x3, it's exactly like multiplying each vector by its coordinate. So it's going to be the first vector, okay, here's the first vector times x1, that's the first vector times x1, plus multiplying the second vector times x2, and so for the third vector. That's the details of the multiplication process. This slide summarizes the link also between the linear combination and the multiplication of two matrices, regardless about what A stands for and what X stands for. So if I want to multiply, if A is given to me by this matrix, and the X is 1, 2, 3, I can look at it. And this is the matrix of transforming, of change basis. and 1 to 3 as the elements of the coordinates, and the multiplying them simply will be the first vector times 1 plus the second vector times 2 plus the third vector times 3. So simply, it's exactly like the previous problem. You will have them on this form. The first vector times 1, the second vector times 2, and third vector times 3. It's very, very simple. So this is how it is in front of you. And once more, shortly, this is the coefficients 1, 2, 3. And this reality connects the linear combination of vectors, matrix of basis change, and the coordinates with the column space. So I can look to the multiplication of matrices and this reality in front of you. Okay, once more, taking advantage of the knowledge of the null space, and with all of this information, I can translate it into a solution of a system of equation. And I can summarize all of this in this form. So connecting the null space with a particular solution of a system of linear equations. Okay, I can use the following. If I'm solving not a homogeneous system, but any system Ax is equal to B, and it is a consistent system, it will be consistent if X, B belongs to Rn, is a particular solution of the system. And the general solution will be on this form. A particular solution plus the null of A. Once more, the null of A, it is the solution of the homogeneous system. And this is, of course, a general solution, as I told you. So once more, that's for each xh belongs, or the homogeneous solution belongs to the null of A. We have xb, which is the particular solution, plus the homogeneous solution of the system. So if I have a system, Ax is equal to B, where A is given by this matrix, B is given by 6 and 9, and I'm trying to get the general solution, is going to be simple. All I have to do once more is to get the augmented matrix, where this is the A matrix, the coefficient matrix, 6 and 9 are the result matrix. And then I will try to get a reduced echelon form by replacing rows and playing with the general properties of row. I've ended up having this reduced form. If you try to analyze this reduced echelon form, it means that's the x, y, and z, which stand for x is equal to 9 minus z, and y equal to 2 plus z. That's the solution that we are talking about, which is, and also of course, z is equal to its value, which is z. If I tried to separate this solution, so the solution set can be easily written as a vector. Let me write it as a matrices. This is going to be the matrix, which is 9, 2, and 0, plus the z or whatever, which give infinite number of solutions, of negative 1, 1, and, negative 1 and 1, and 1, the last element, because this is negative z plus z plus z. If you look at it, this is the null solution. This is the null space. And that's the particular solution that we are talking about. Now, we can explain the system or the solution of a system in terms of the null space. So once more, as I told you, expanding the last equation will be x1 plus x3 equal to 9. x2 minus x3 is equal to 2. So once more, I have x1, x2, and x3. Replacing x1 by 9 minus x3, x2 by 2 plus x3. I will have this set of solution, first coordinate, second, and third. I can separate it with 9, 2, and 0 for the particular solution, and negative x3, x3, and x3 for the null of A, as you can see. So it's simply 9, 2, 0 plus x3 or z times negative 1, 1, and 1. And so this is exactly the particular solution plus the null solution. So 9, 2, 0 plus k times negative 1, 1, and 0. Based on this fact, we can simply write the solution once more, to write the solution or the classification as it's gonna be. A solution of a system of equations, AX is equal to B. It's gonna be consistent just on one condition. If B belongs to the column span of A. So if the column B belongs to the column span of A, there will be a solution. If not, there will be no solution. It's an inconsistent system. Okay, if B belongs to the column of A, so it's a consistent system. If dimension of null of A is equal to 0, which means the null space is equal 0, 0, and 0, in such a case you will have inconsistent, just only a unique solution. But if the dimension is greater than 0, then the span of the infinite number of solutions already exists, and so you will have infinite number of solutions. I made it once more for you, stating the fact that that's the solution set with the particular solution plus null of A. If B belongs to the column space of A, then you will have a consistent system of equations. If the null A is the homogeneous solution of the AX part, and if null of A is equal to 0, you will have a consistent independent. Otherwise, null of A exists, so you will have consistent dependent system of equation. This classification is really very important because you will be asking about this either in multiple choice questions or in questions that you will fill as you saw in the previous exam. All of these statements are equivalent to each other, which is really very important to memorize. That the rank of A is equal to n, that means you have a unique solution. It is A invertible. Of course, it will be invertible because once the rank is equal, the rank of A is equal to the number of unknowns, you will be able to reach a reduced echelon form on a unit matrix, and you will have a solution. If A equal to In, so as I told you, you will have a unique solution. It means also the null of A will be 0 because you will have a unique solution. The column of A will equal to the row of A equal to Rn, so the dimension, if this is R3, the rows will be 3 and the columns will be 3 since the null is equal to 0. The rows of A as vectors of Rn form a basis of Rn, and also the columns of A as vectors of N form a basis of Rn. Those statements are very important. You will find them on the main slides, and also I've sent it to you in the updated slides that we are working on. If we go into a linear transformation, we can link all of these informations also with the linear transformation if you remember it. Because simply, we can find simply the matrix that moves the stuff from, or maps the stuff from Rn into Rm. And it will have a dimension. So a map from Rn into Rm is called the linear transformation if there is an m by n matrix. So I now can form the m by n matrix. I want you to review all the lectures of the linear transform. It's well explained. You will find them on YouTube, so study them first and then continue. Remember that for a transformation, or a linear transformation, we will have the matrix of the linear transform times the vector of x, which is gonna represent the energies. So once more, remember linear transformation, similarity with AX, it's a solution of a system of equations. I want you to know that the kernel of T, we already defined the kernel in the linear transformation, it's the solution of the images or the images that will tend into 0, which is completely like solving a homogeneous system, A times X equal to 0. So this is an important, very important statement that the kernel of T is equal to the null of the matrix of the transform. Also, I have n minus dimension of null of A equal dimension of row of A, as you saw and as we've proved or hold in the previous two examples, with the reality that the dimension of row of A plus dimension of null of A is equal to n, which is the dimension of your vector or subvector space. We found also that the range of T, which is related to the linear space, is equal to the column of A of the matrix of the linear transform. Finally, if you have the dimension of null of A plus dimension of column of A is equal to n, and dimension of kernel of T plus the dimension of null of AT, and the dimension of range of T is equal to the dimension of the column space of this matrix. So the kernel plus the range is equal to M. And this is based on these two equations in front of each other. Also, this slide is really very important. And the parts in it, which part is equal to which part, or which space is equal to which space, or to what space is really very important. Also, from this, the terminology of injectiveness is really very easy. A linear transform is going to be injective if the dimension of the kernel of T is equal to 0, which means it has just only the 0 vector. That's the unique solution or uniqueness. So the dimension of null of A is equal to 0. And T is surjective if and only if the dimension of kernel of T is equal to n minus n, which is the difference between the cases of n and m, or the rows and columns for the dimension, the matrix of the linear transformation. It's the dimension of the column minus the dimension of rows or the row space. N minus m, as you can see. So this slide also is really very important. Okay, as I told you, it will give an infinite number of solutions. All of the previous remarks are shortly explained here. The kernel of T is equal to the null of A, range of T is equal to the column of T, the kernel of T is equal to the dimension range of T plus dimension range of T is equal to n. It's injective if and only if the kernel is equal to 0. It's surjective if and only if the kernel of T is equal to n minus n. This is very important, as I told you, and you will have to memorize these relations. I'm sorry for the number of remarks and propositions, but this is really a very important chapter, as you saw. Okay, to the exercise part, you have plenty of problems. I've tried to solve some of them for you in this section or in this lecture, and I will continue within the next lecture, inshallah. Here, he's giving you, let S be the set of matrices n by n. So S is a set of matrices n by n that commute with a matrix B. So it's the set of certain types of matrices that will be, what's the meaning of commute? Commute means if A times B, it will equal to B times A, which is a very specific property. To prove this, I can do it very, very easily. I can say that B belongs to the n by n, which is a square matrix, as a function in R, and divide S as. So I'm talking about the set of all matrices that will commute with B. That's A times B is equal to B times A. I'm talking about the set of matrices of A. Okay, this is easily proven to be a subvector space. First of all, in order to show it's a subvector space, we need the three things, if you remember. The origin that exists with this subvector space, the addition closure, and the multiplication by scalar closure. So, non-empty set, the zero matrix satisfies this relation. If I have a zero matrix, A is zero matrix, so 0 times B, it will be equal to B times 0. So already you have your origin. Number two, the closure of the addition property. If I have two matrices belongs to this set that commute with B, so AB will equal to BA, and for the second matrix, BP is equal to PB. Hence, from this, I can prove simply that A plus B is equal, times P is gonna equal to this reality. I can replace them since they are commute and taking B as a common, and so this proves the addition of the existence of the addition property in this class of matrices. Similar to multiplication of a scalar value also will be hold with the commute with matrix B and A. So it's already proven from these three steps that's gonna be scalar multiplication and the addition, and so it's a subvector space. So for number one, it's proved. Now, for n is equal to 2 and the B is exactly the matrix 1, 1, 0, 1, I want to find the basis for S. I can find many bases for S, actually. I can say that's the matrix P that we are talking about. So I can take the canonical form, which is 1 0 0 0 1 0 0 0 0 1 and 0, and I will be able to do whatever I want with it. Okay, that's a set of 3 matrices, and the vectors, he's asking you about the coordinates that will work with this basis in order to get this matrix. Okay, the coordinates is very, very simple. Multiplying by 3, then by -2, then by 3. So the coordinates are simply 3, -2, and 3. This is not the only solution. I can do another solution. Here, since these 2 elements are equal to each other, I can choose a different basis. I can choose 1 0 0 1 and 0 1 0 0. And in this case, the coordinates are not going to be 3 coordinates. I can multiply either winner coordinates 3 and the -2. So the first matrix will be times 3, and the second matrix will be with the -2, and these are the coordinates as you can see. Now I've answered B and C. This problem is very good. It's taking you from how to hack or to find the basis, how to prove it's a subvector space, how to get the coordinates in this case. This matrix, this problem also is very, very nice. He wants you to show the solution set of this system of equations, and he wants you to find the kernel of this linear transform from R3 into R2. That's the function of the transform, and you already know about how to get the matrix of the linear transform. This is the orthogonal complement of the span of these 2 vectors, how to bring it. All I have to do is to multiply x, y, z times x1, y1, z1, which is going to be the first equation. Multiplying x, y, and z times 0, 1, 1, which is going to equal to 0, which is the second equation, one solution. And the null space of this system, which means a times x equal to 0 also. So those are the remarks that we already know, that the kernel of t is equal to the null of a of t. Row of A orthogonal is equal to null of A. That's the null space of A, the solution of this system. So I will get the augmented matrix. I'm solving a homogeneous system. I'll try to put it on a reduced echelon form simply by multiplying by -1 and adding on the first row. That's the matrix that you will have, which means x is equal to 0 and y is equal to -z, as you can see. So the solution set is taking x by 0, replacing y by -z and z. So simply the span will be 0, -1 and 1. In a similar manner, the kernel of t, it is the null solution. So the kernel is having the image of this linear transform, these 2 guys, and putting them equal to 0, which once more, it will be ended up with having the same system of equations like those. Solving it will lead you to the span with 0, -1 and 1. For the third, he wants you to find the orthogonal complement. Once more, multiplying x, y, and z in 1, x, y, and z 0, 1, and equal to 0, you will have the exact same system, and the orthogonal complement on this span is 0, -1 and 1. And also the null space of the matrix 1, 0, 1, and 1, it's exactly like all of this. So in all of these, in all of these requirements, the solution is 0, -1, 1. This is really very important problem. I want you to go through it more than once. It's already solved in front of you. Now I want you to remember the difference between a span and the basis. Span, it means a set of vectors with all possible linear combinations that will generate a certain vector space. So span is the entire subspace generated by those vectors, like 1, 0, 0, 1, or 2 will give R2. Also, for the span, I can use 1 and 0, 0, 1, 0, 2, 2 and 0, and will generate the same span. Okay, the basis, it is the optimal set. So the basis, it's a subset from the span. It may equal to the span, or maybe less than that. In this set basis, all the vectors are linearly independent, and they can generate your vector space. So that's a small comparison between them. That's the span, and that's the basis, and the cases are in front of you. Shortly, span, it is the space, it is the space you get from combining vectors. Basis, a minimal. It is the minimal span that you can use with an independent set. Or more simply, basis is a subset from the span or equal to it. And the span of basis is equal to your subvector space. This slide is very important. This problem also, it's about linear transformation from R2 into R3. You will have the function of your linear transform. He is asking you to find the dimension of the kernel of T, which is very, very simple. All I have to do is to take these three equations equal to 0, put them in a system, and to try to solve this homogeneous system and find the rank, and find the relation connecting them. I will be able to find the kernel. Find whether any vector of R3 is an image of vector in R2 or not. And also, it's going to be really very simple. All I have to do, as I told you, is to solve the system x, y, x minus y, 3y minus x. If you try to do so, this is the system of equations that you will deal with. Try to simplify it as much as possible. As you can see, you will have a unique solution. Therefore, the kernel of T is equal to 0, and the dimension of the kernel is equal to 0. That will leave you with the dimension of the range is equal to 2, the set of this transform. And also, once the kernel is equal to 0, it means this transform is injected by the rank inequality theory. Is every vector of R3 in the image of 2? No, of course, because you ended up now having just only rank of 2, which can represent, as I told you, the rank of T is equal to 2. Images is with two-dimensional subspace. It's a plan of R3, not all of R3. This problem also is very good. As I told you, this is the standard R2, and here is an example of 1 and 0, and 0 and 1, how it's going to be represented over there. That's another problem. For solving a system of equation Ax is equal to B, find the basis of the column, of the rows, find the null basis, and also show that the system is consistent, and give examples. This system first, it will be solved by Ax is equal to 0. I will put the system, I will try to put it on the reduced echelon form. Now I have the rank is equal to 2. Based on this, I have the dimension of the column space and the dimension of the row space if I want. So here's the dimension of the column space. That's the dimension of the row space. And basis for the null space solutions of Ax is equal to 0. I can find it. So the span is -2, -3, and 1 for the null space. Now I can find B, which is consistent system. B first column of A. It will be a consistent if you just take B equal in the plan. Belongs to the span of the column space. So I can take the B is equal to 2, 3, and 1. And if you choose any value that doesn't belong to 2, 3, and 1, it will be no solution for this system and will really exist. Thank you very much for holding up with me through this lengthy lecture, but it's a very important lecture. Thank you very much, guys, and please try to study well during the next period. The exam is gonna be on next Sunday, so I need you to focus, and inshallah everything will be fine. Thank you very much, and hopefully you will be able to review this information. Thank you. If you have any questions, you know you can come to me, or send a message or send an email or anything. Thank you very much. See you next time, inshallah.